this afternoon and a little bit yesterday as well. And there has been some conflation of these terms by one person in particular. And I want to be really clear about what I mean by space archaeology. I am not talking about satellite remote sensing for terrestrial archaeology at all. What I'm talking about is an archaeology of human activity in outer space. And that's really, that's not my coming up with that definition. There have been people working on this since at least the late 1990s. The very first space archaeology project that we can point to of any scale was Beth O'Leary at New Mexico State University, who did a survey of Tranquility Base, which just celebrated its 50th anniversary in July, and she was able to determine that there were 106 objects left behind there by the astronauts of Apollo 11. And this is something that actually various people have been working on. So when we talk about space archaeology, we're talking about human activity in space. This paper describes the first large-scale archaeological investigation of a human habitation site in space, the International Space Station Archaeological Project. The development of society and culture in a microgravity environment for which our species is not evolutionarily adapted has never really been studied before. Space agencies are increasingly concerned with carrying out long-duration missions, and for decades they have studied the physiological and psychological consequences of human spaceflight. Only negligible attention has been focused on theorizing about, yet not investigating, social and cultural aspects of life in space. The genesis of our project came in November 2015 with NASA's most recent call for new astronaut candidates. The advertisement stated that degrees at any level in, quote, social sciences, open parenthesis, geography, anthropology, archaeology, etc., close parenthesis, were not considered qualifying. There has accordingly never been an astronaut with a humanities or social science background. The co-PIs, that is to say, Alice Gorman and myself, who have worked to develop space archaeology since 2003 and 2008, respectively, decided to perform a study that would demonstrate the relevance of the social sciences for space mission design. This is a perfect place to be talking about this. Material culture has been shown to be an excellent way to examine social and cultural life in both past and contemporary societies, and particularly to reveal aspects of life that cannot be studied in other ways. We identified ISS as the best candidate for investigation due to its extensive occupation and the likely array of available evidence. 239 people from 19 countries have visited the space station since November 2nd, 2000. In fact, last Saturday marked 19 years of continuous habitation of the space station. 120 people have lived for periods longer than 2 weeks on ISS. The station is likely the most expensive building project ever undertaken by humans, costing as much as $150 billion US to construct and maintain. Most importantly, the crew of a spacecraft was already recognized in 1972 as, quote, a micro-society in a mini-world. I love this phrase when I'm thinking about spacecrafts and archaeology. It absolutely encapsulates what we're interested in. But we cannot visit our chosen site to conduct field work. Even if permission were gained from a space agency, current estimates of sending a single archaeo astronaut are around $75 to $80 million US. I don't think we can get any grants for that. We'd like to try. The inception of ISS habitation on November 2nd, 2000 fortunately coincided with the rise of digital photography, and thus NASA has an archive of millions of images, which they started sharing with us only a few weeks ago. And this has been an 11-month process since we got our grant from the Australian Research Council to finally, receiving images. In fact, while we were at lunch, I got an email saying we got a new batch, so that's really exciting. But in any case, those images mostly include metadata encoded in their files, recording the time and date that they were made. And these are just examples of the kinds of images that we have. We can therefore observe changes in the material culture of ISS over time as people and things moved around the station. The metadata become the metaphorical stratigraphy of our excavation. The images are an untapped resource that will allow us to capture an unprecedented view of the society and culture developed and perpetuated by the international, multi-ethnic, multi-gendered, and multilingual crew. Among the questions we plan to address are how people adapt their behaviors and tools to the specific requirements of life in space. Here's an ESA astronaut, Samantha Cristoforetti. Particularly how spaces or tools diverge from their originally intended functions. We're interested in how objects are used to negotiate power and identity, including the gendered use of spaces and objects within the space station. Other questions include how do crew members interact with each other and with the equipment and spaces originating in other cultures. Using archaeological approaches to culture contact and confined contexts, similar or analogous to a space station, we will gain insights into how the multicultural crew adapts to the unique living conditions of a microgravity space station. In June 2017, we teamed up with this paper's third co-author, Dr. Eric Lindstedt, to leverage his expertise and experience in machine learning approaches for extracting data. Machine learning has already been applied successfully to build intelligent models of biological, chemical, physical, and medical systems. Archaeology, and maybe especially space archaeology, represents an opportunity to apply these techniques to a domain that so far has yet to benefit from the power of AI. The machine learning approach appears likely to be most effective for rapid identification of the crew members and spaces within ISS, but we'll talk more about that in a second. By using machine learning techniques, we're able to rapidly and accurately convert non-machine readable source media to machine readable and analyzable data for our database. Once the database is complete, we are mapping the movements of objects and people around the modules over time. We will identify patterns of activity and movement, and statistical software will be used to calculate patterns of distribution for objects and people in space during particular types of activities. And I just want to use this as a very brief example, a little discursus here. This is an image that caught my eye as I was kind of practicing doing a pilot study for how we would capture data initially manually, I was thinking. And so here we have on the left an American astronaut, in the middle a Japanese astronaut, and on the right an American space tourist in a Russian module, and you'll probably already have noted the objects that are on display on the back wall behind them, which include Orthodox icons, a gold cross, a Russian flag, mission patches, and photographs of Russian space heroes, particularly Yuri Gagarin, the first human in space, and Konstantin Tsiolkovsky, a little bit lesser known, but the man who first, in the 1920s, theorized what life would be like for humans in microgravity. So those are the photographs that are there. There's also a small painting over here, that is actually a painting of the most important church in Russia. And so we have a whole space here in the Russian module that is really dedicated to a display of Russianness in an international space station, and yet here we have 3 non-Russian crew members. That just, how do you capture that information? So initially I was kind of working with a SharePoint database to see, like, how do I capture that? How do I capture spaces and people? So, activity category leisure, what are they doing? They're holding on to each other. Where are they located? So crew member location, and this is within the photograph, upper left, lower right, and middle ground. In other words, all of the parts of the image, but also where in the space station. So the module, the Zvezda module, is it the fore or aft, top or bottom, or port or starboard part of the space station? And so that's kind of how we're thinking about dividing this up, because we cannot use georeferencing in a spacecraft that's traveling around Earth at 28,000 kilometers an hour. We have unique challenges in this site, in any case. So thinking about those issues and then realizing how long, and it would take me probably 4 hours to do a single photograph by hand, that with the number of photographs that we had, it was never going to work unless we could automate the process. So, machine learning. We've heard the same basic paragraph over and over again the last 2 days, but here you go again. In recent years, the hype surrounding artificial intelligence has grown exponentially, despite the fact that the field itself dates back to the 1950s. This resurgence in AI has been driven in large part by advancements in machine learning, which focuses on finding patterns in vast volumes of data. The maturation of the internet, combined with ever-increasing computing speeds and decreasing data storage costs, has paved the way for AI algorithms to be deployed on a scale never before thought possible. Most recently, deep learning, machine learning algorithms inspired by the organization of the human brain, has taken center stage for AI researchers and practitioners, achieving better results on previously solved tasks and solving tasks such as playing the game of Go with human-level expertise that were never before believed to be tractable. Our work leverages the current state-of-the-art techniques in deep learning, specifically related to computer vision, to provide for the computationally driven classification of imagery from the space station. These classification tasks include determining what objects appear in an image, which astronauts appear in an image, and when combined, how these things and people are correlated in the overall corpus of imagery. To achieve this, we apply convolutional neural networks, CNNs. Given sufficient data, these networks are capable of learning features in imagery that correspond to the presence of certain objects or people. At a conceptual level, the networks themselves operate similarly to how the human visual cortex digests and organizes visual stimuli. Convolutional neural networks form the basis for a variety of contemporary autonomous systems, including self-driving cars. Most importantly, these networks can be trained efficiently using commodity computing hardware. The availability of pre-trained networks, as has already been amply discussed, further facilitates the application of CNNs. One of the most popular training sets for these pre-trained networks is Imagenet, which has been calibrated on over 14 million images belonging to thousands of categories, and maybe more. This is actually more germane to what we're doing than maybe what anybody else here is doing. But we have, for a pilot project used to hone our techniques and approaches, applied an Imagenet-based CNN using the VGG16 architecture to roughly 7,000 publicly available ISS photos curated from NASA's Flickr page, which you see here. So they have about 25,000 images in total, showing all aspects of training, launch, work inside and outside the space station, returning to Earth. Of those 25,000, about 7,000 show the interior of the space station. So we've selected those. No attempt was made to customize the network to our data. Rather, we wanted to determine a baseline using an off-the-shelf network that could be used to measure performance of custom networks trained in the future. In one set of experiments, we classified images exactly as downloaded from Flickr. In the other, we partitioned the image into smaller regions, chipping them, so that each region contained a smaller number of objects. Our empirical results indicate that a pre-trained ImageNet model without customization is able to effectively identify salient objects in ISS imagery when large images are broken into smaller regions and each region is classified in turn. Essentially, we've got two rows and 3 columns, so 6 chips per image. For example, we were able to correctly identify photos containing laptop computers, food, cameras, tools, and maps, and these are some examples. So you've got the actual chip on the left, and then you've got the classification activity map on the right showing what it was keying in on, and you see the predicted tags. Spot checking on a random subset of images suggests high accuracy of 80 to 90% for common items, such as computing devices, such as displays. However, we are currently curating a large test set with human-validated ground truth labels to more systematically assess accuracy on a large scale. Naturally, there were many in this classification. So you're seeing good ones here where it basically got the answers correct. Right? Meal, food, breakfast, bread, lunch. For example, as a misclassification, a pair of scissors being held vertically with both blades not clearly visible was classified as a syringe. These types of errors are merely an artifact of the image angle and are not specific to the space domain. Other misclassifications, however, are due to the fact that specialized hardware on ISS is not accounted for within Imagenet and therefore is mapped to one of existing categories. When classifying larger images, the CNN tended to put focus on the presence of people or classify collections of objects into the broad category of machinery. This suggests that image pre-processing will be critical to our future work in order to gain increased specificity in our classifications. In our next experiments, we will use Imagenet for transfer learning, but also retrain the network to use labeled data for specific space objects. This should improve classification accuracy on more specialized items. Alternative CNN architectures such as region CNNs, which we've heard about yesterday, may also prove to be a viable direction, though a challenge will be to correctly define object bounding boxes when many different types of objects of varying sizes appear in the image. More important than the specific network architecture, however, is the fact that the time to tag an individual image, less than a second, far surpasses what is achievable by humans. In addition to our object recognition tasks, we trained a convolutional neural network based on the VGG architecture to predict the identity of crew using several hundred labeled photos of ISS astronauts curated from Google image search. Our results once again indicate that CNNs are able to accurately differentiate between ISS personnel, especially in imagery where faces are not occluded or obscured by other objects. For example, the network was able to identify Roscosmos cosmonaut Gennady Padalka and NASA astronaut Scott Kelly with over 80% cross-validated accuracy. In the future, however, it will be necessary to train on a much larger data set containing as many poses as possible in order to increase the ability of the network to generalize to situations when not all facial features are clearly visible. So here you see, because Scott Kelly, who's on the left, has his head turned to the side and has his hand up, it did not accurately recognize him. In this work, we've established that based on, here's another corner case specifically for Scott Kelly, that he has a twin brother named Mark. That's probably not going to come up too frequently because Mark only visited the station once for a few days. But in this work, we have established a baseline for the application of deep learning in order to automatically process and annotate imagery from the International Space Station, with a focus on pre-trained models using commodity hardware. In our future work, we will build more specialized models tuned specifically to ISS data. This will require leveraging image metadata and other annotations to determine ground truth. Training these specialized networks will also necessitate moving to high-performance computing infrastructure. However, based on our initial results, we are confident that we can build a machine learning pipeline to accurately tag people and objects in ISS photography with the ultimate goal of understanding the relationships between them. Thank you. I didn't do any of the machine learning stuff, so it's really technical. I might not be able to answer. Fair warning.
Thank you. It's nice to see some anthropological angle to this. Any questions?
So, I was just thinking in terms of deriving the meaning from the images, in terms of context. Is it possible to work, are you going to work backwards once you've identified the objects to understand where and how they're being used, so it sort of gains that value?
One of the other things that is going to be really key for what we do is understanding what kind of association there is between people and objects. So there are really two kinds of issues. First, if you've got objects that are associated with people, they're holding them, they're eating them, they're drinking them, they're experimenting on them. And then there's the objects that are in the image but are unassociated with crew members. And we are definitely going to have to go back and identify those relationships in each of the images. Yes, that is something that I don't think we can deal with machine learning. But we will have all that other data in there. And for the unassociated objects, we will simply be able to track them through time. Leaving aside the objects entirely, I would say we've got some really low-hanging fruit when we just talk about identifying people in spaces, because we will be able to say almost immediately, are there gendered spaces in the space station? Are there areas of the space station where women are seen more frequently than you would expect based on their proportion of the population than men, or vice versa? Are there national spaces of this international space station? Do Russians hang out in one area, Americans or Japanese in another area, etc.? And by the way, we can also expect that that's going to change because the configuration of the space station changed over time as it was being built during basically the first 10 years of its existence. So yeah, there's lots of rich aspects to this that we're going to have to dig into. Yeah.
Thank you. That was a very interesting presentation.
Thanks.
I was wondering from an ethnological point of view, the anthropologist tries to disappear, to merge in the culture and observe. But in this case, those they were the people in the pictures were very conscious. Pictures of them were being taken. I don't know.
Yeah.
I'm thinking of situations like a Russian astronaut drinking Coke, but if there's somebody taking a picture hiding it, you know, how
So,
are you dealing with the fact that those
Okay.
are to represent people are actively trying to represent?
So yeah, your point is well taken. I mean, I think the key part is what you said first, that the anthropologist tries to disappear, but of course we know that that's not possible, right? The presence of the observer always changes what's going on. And in this case, they don't know they're being observed by us, but they know they're being observed, right? What we know is that on an average, 400 pictures are being taken per day. We are not getting access to all of those. So there are different levels of photography. There's the photos that are available on the Flickr page, which not only don't portray anybody in a bad light and always show them smiling, and actually, I can tell you from having looked at all 7,000 images, fall into like 6 categories. They're information, you know, like we saw the 3 guys, they're flying in some special formation like Superman, they're eating, they're drinking, they're doing an experiment, they're looking out the window, and that's about it, right? Because that's what NASA Public Affairs wants us to see. And one of the biggest battles that we had over the last 11 months getting those pictures was getting them to understand that that's not enough, that we need to see as full a range of images as they possibly can give us. What I can tell you is that, for example, they're not going to give us images where an astronaut might be in a state of undress. They're not going to give us ones that make them look bad. I haven't yet in the images we've gotten seen whether we've gotten blurry images. Those are the ones that also don't tend to get released. What we are going to see that the general public doesn't see is images that have commercially proprietary technology. Right, because NASA and the other space agencies have agreements with various companies that put technology up there. We're not going to let anybody see this because it's just secret technology. Not that it's classified because obviously it's international, but you know, Anheuser-Busch put a barley experiment up there to see what beer in space might do. Whatever. They're not going to show those to the general public. We will see those. We cannot release them to the public, but we can use them for our research. So there, you know. We are going to have to manage the bias in there, but the bias is not going to be as bad as what we see in the Flickr images. But you're absolutely right. It's something we have to think about. And then another thing we can do is, obviously, we can talk to the crew. We can say, here's a picture. What do you think is going on here? And they might not say what we expect them to say, but they might not say what we see happening there. And that's going to be interesting as well. There's a lot to do here. Yeah.
Thank you. There were some more questions over there.
I had one.
Yeah.
Okay. Thank you very much. Maybe this is self-explanatory or obvious, but with the machine learning to identify individual astronauts via image recognition, I'm guessing there's not, but maybe there are any examples where in the database you'll get the record of who that is somehow has vanished. So they might be interested in then you applying these techniques to see if you can restore, it's likely that that person in that image is actually this astronaut or cosmonaut, but somehow we lost the label or the note about that image or something.
I think that's incredibly unlikely
Okay,
because,
figured as much.
as I said, there's only been 239 people who have gone to the space
Right.
station, and the space agencies have gone to extraordinary lengths to make those people public figures.
Right.
So there are actually tons of very good images of them available, Google image search,
Right.
that we can use to do the training. That's got their name attached to it. That's going to be actually the least of our problems, I would say. Yeah.
Right.
It's the objects that are going to be harder, like the scissors syringe thing. That's really going to be a challenge, I would say.
So just a quick one. When I saw the title of your presentation, so when I think of space archaeology, you know, after Sarah Parker, the first thing that comes to mind is the first thing that comes to mind is space debris.
Oh yeah.
So that could also be an interesting, you know, to see. I don't know, because a lot of historical since the beginning of the space age. That's interesting.
So for those of you who do not know my co-PI, Alice Gorman, she is popularly known as Dr. Space Junk. That is her Twitter handle, and I definitely suggest that you follow her because she's awesome. And that's really, up until this project, that's what she's been working on, the cultural significance of space debris and of early satellites and things like that, as well as launch sites around the world. And by the way, when I say human activity in space, as space archaeology, that also includes facilities where humans performed actions on Earth that were directed at space, like Cape Canaveral or Kourou, the ISSAP launch site, or Baikonur in Kazakhstan. Those are also part of space archaeology that are here on Earth. But yes, space debris is a huge issue because at the moment, U.S. Joint Space Operations Command is tracking 24,000 objects that are all moving 28,000 kilometers an hour. And for example, in 1983, the Space Shuttle Challenger was hit in the windshield by a 0.1 millimeter fleck of paint that almost cracked the windshield completely. So these are really dangerous things, but nobody's figured out how to get them down. And on top of that, some of them are culturally significant. Like the oldest object that's still in space dates to May 1958. It's still up there spinning around. That's Vanguard 1, the US satellite. Sputnik is no longer up there. But there are really historically significant objects up there, and we might want to think about how we're going to preserve those. That's a different topic. Yeah.
Great, thank you so much.
Thanks.
And so we move on to the final speaker of today, Hector